Great. Well, thanks so much, Ebba, for your kind invitation to come and visit the Pufendorf Institute here at Lund University. Wonderful town. I had a little walk around last night. It's very different than Los Angeles, to say the least. But I hope anybody who's visiting Los Angeles will come and look me up while you're there. What I want to talk about today really has inspiration in a famous geographer who worked here at Lund for many years, and his name is Hagerstrand. And I'm going to try to link this to some more modern terms that relate to the exposome. So let me give you a map of my talk. As a geographer, I always like to give maps, even if they are just in words. I want to talk a little bit about the concept of the exposome and the need to extend that to what I would call external measures rather than just taking biomarkers in the body. And then think about the time geographies of exposure and the lifeline of exposures as sort of a prelude to the exposome. And then I want to talk about some new and interesting developments that are occurring in what's called a ubiquitous sensing or a UbiComp world. And in keeping with the Africa, air in Africa and cities theme, I'm going to focus mostly on air pollution examples. And I'm going to look at how we can use smartphones as sensors, standalone microsensors, embedded sensor networks, and satellite remote sensing, and then try to draw some of the key conclusions and challenges. Before I get going, who's heard of the term exposome here? I just want to... Okay, so I'll spend a little bit of time explaining that then. So this was a term that was first coined by Christopher Wilde, who's now the director of the International Agency for Research on Cancer, that works for the World Health Organization to designate whether substances are carcinogenic or not. He's a toxicologist, and he made a plea in 2005, which really wasn't picked up until about 2010, 2011, when two of my then colleagues at UC Berkeley, Smith and Rappaport, wrote a science article on it. But the idea is that we want to be able to measure the exposures that somebody experiences with the same precision that we can measure their genome. So we want to be able to characterize their exposures from conception to death in a great deal of detail. And he split it up into three major areas. So the sort of general external, so social capital, education, the internal, which might be our metabolism, endogenous hormones, and I'll let you read the rest, and then specific external, radiation, air pollution, things that we're familiar with when we think about traditional environmental exposures. And in a subsequent article, he basically outlined all of the various technologies that might be used to characterize the exposome, and you can see them up on your right. And he, I think, was trying to conceptualize the exposome as a discovery mechanism that would identify underlying hypotheses that we might not be able to understand if we took a very doctrinaire, structured approach toward understanding how an exposure affects health. So you might think, well, we have past evidence that it affects inflammation of the lungs, so I'm going to hypothesize that air pollution affects asthma development or something like that. But there could be a whole range of cumulative exposures and cumulative outcomes that we may completely miss. So his idea was to take this vast array of data on the exposome, combine it with the genome data, and do data mining so that you could then identify new risk factors that you would take into this more traditional way of looking at exposures and health effects. So there's been a lot of debate since he first published that article and the Smith and Rappaport article in 2010 about whether you could just characterize the exposome based on internal measures. So we would take biomarkers and then look at what's in someone's metabolism, look at their hormones, look at the contaminants in their body, and then say that's it, that's all we need to know. And that's certainly the view that my colleagues took at Berkeley. I used to argue with them in public all the time at the National Academy of Science. It was kind of fun, you know, saying, well, we have these arguments all the time at home, we may as well take them out in the public. The other view is that, you know, we need both an internal and an external assessment because all measures of exposure are flawed. Now, some are useful. We've all heard that joke about, you know, statistics all being flawed, but some are useful. It's the same with exposures. And I think also when we think about external, it emphasizes what's known as a prevention mode. because we need to know what's coming from the external environment if we're going to identify sources that will then be used to control exposures. So I think, just before we go on, I want to emphasize why we do need these external exposures. And I think, when we look at it, a lot of the most important exposures have no specific biomarkers, and they're often context specific in time and place. So noise, electromagnetic radiation. Here's a classic article by Gutsky, where he looks at the various determinants of noise exposure. So we have some sound pressure that's coming to the receiver. The individual then perceives that, and the perception is determined a lot by whether they think this is a justified exposure, what the situational parameters are, whether it affects their ability to talk to others, whether there are other stress factors. That then leads to some sort of neurological and endocrine activation that leads to an annoyance that can then translate into acute and long-term health effects that eventually affect health and quality of life. So here's an exposure where if you were just measuring it internally, you wouldn't really have anything to go on. You might be able to look at a very general stress hormone like cortisol, but you wouldn't be able to say, aha, I know it's noise, or aha, I know it's that particular type of particle. Another reason is that biomarkers can have very short half-lives, and they don't capture peak and subchronic exposure, so organophosphate, pesticides, ozone. A lot of the biomarkers are often evacuated out of the body within a matter of 24 hours or less. So what you get from that internal measure is simply going to give you the snapshot in time of what the person experienced very recently. And it's not necessarily going to characterize that long-term exposure that we might be interested in for chronic health effects. And that many substances are well below limits of detection. So in current blood analysis, we might miss about 90% of the known pollutants. So, things like benzene that we know are carcinogens, we can't detect them all the time at the levels that they appear in the blood. And 30% of those endogenous and food chemicals that we generate internally would be missed as well. And then we know that these exposures often occur in complex mixtures. So these mixtures themselves may elicit health effects, but they also might operate on very similar pathways. So here's an example. Say we're interested in air pollution. Well, clearly oxidative stress is a key mechanism by which we think it affects the heart, lung, and brain. But it also has other mechanisms that affect hormonal regulation, regulation, specific effects that may overlap with allergens. So you can see from this nice diagram that Annette Peters and Gerhard Hoek put together that it's really going to be very difficult to identify the exposome and the exposures if you just look at the internal biomarkers. And then just hearkening back to this prevention mode, if we're going to prevent disease, we need to know the sources, because that's what we control. So it's critical that we would be able to understand where they're coming from, because that also might condition the social response. If it's polycyclic aromatic hydrocarbons from cooking too much meat versus diesel exposures in the ambient, we may not want to regulate what people eat, or we might want to give them educational information, but we would definitely want to regulate those exposures that are being received involuntarily by individuals. So if you want a summary reference on this, my colleagues and I just published this last year in the Annual Review of Public Health, and it makes a lot of these same arguments and goes through some of those exposures in great detail. So I think when we think about the exposome, what inspired this? It's the idea that individuals are moving through time and space from, say, the point of conception to their death, and that we might be able to actually measure where they are. And we might be able to understand the exposures as they're moving through these hazard fields. And I think in this way, the great geographer from Lund University, Hägerstrand's idea of time geography is sort of a critical concept for the exposome. A lot of people that do exposomes have never heard of Hägerstrand, but because I'm a geographer, I've studied his work in great detail. And it's amazing, really, that he came up with most of these ideas in the 1960s and 70s, long before we had the computing capacity to ever think of how we might quantify it. And that's going to be one of my themes today. Are we there yet? can we quantify this lifeline of exposure. But if we think of exposures, he called them hazard fields. So it's a summation of travel through hazard fields. And here we have an individual that's moving through time and space. And then if we characterize the regularity of their movements, we might call that their potential activity area. So that we're then able to look at restraining that to this area that, say, they spend 95% of their time in. And then we're going to try to characterize the various exposures that they experience as they go through time and space. So here's a nice diagram, an earlier one from my good geography friends, Briggs and Gulliver, where they look at different pollution maps, and you can think of the person as traveling through these maps, and some of the exposures are going to be longer lived, like the first journey one, but the journey two is going to hit that one pollution exposure and move on very quickly. And how do we go about characterizing that, and what does it mean? And when we look at activity space, there's absolutely no question that it's a major determinant of a person's exposure, particularly to air pollution. And here's an earlier sort of conceptual diagram I did. If we look at Los Angeles is a fascinating place to study air pollution because it has some of the highest and lowest air pollution exposures in the United States. So you can go in 1 hour drive from some of the highest levels, like 25 micrograms per cubic meter, much less than in Ethiopia, where it's more like 60 micrograms per cubic meter, African cities, down to something that's around 9 if you go on to the other side of the mountains. So if you look at those two 95% ellipses for activity space, one could be for a retired person that doesn't go very far away from their home or a child, and the other is for a commuter that's coming in from the far edge of San Bernardino, then into Riverside. So you can see from that the exposures they're going to experience are going to be dramatically influenced by where they are and when they're in those hazard fields. And it's not just about the location of where the person is, but what's their activity level. This is from a study I conducted in Berkeley. It's my current graduate student, Jonah Lipset, who was a research tech working for me. But we basically loaded up bicycles. There have been other studies like this done in Europe. And we drove them around to try to see what difference it would make to go on high and low air pollution exposure routes. And when we look at ultrafine particles, for example, so this is just in 3D, and the blue is the low exposure route, the purple is the high exposure route. And just to put this in context for people that like measuring particles, these spikes are hitting about 1 million particles per cubic centimeter. So these are some of the highest levels I think ever observed in a study. I think that was actually me riding behind a diesel truck and a bus combined together. So in this study, you can see that when we go from the highest to the lowest exposure, that on the high exposure route, it's about 544 times the ratio from highest to lowest. But even on the low exposure route, the ratio is like 135 because that low exposure route occasionally goes across unavoidably busy roads. So there's a very fine microgeography to a lot of the exposures that we experience, and that complicates this assessment of the time activity space and what it means. But if we look at what it also means for the inhalation that a person might experience, it's not just where they are and what the ambient exposure is, but it's what they're doing at that time. So a person who's sitting in a car or very sedentary, they're going to inhale something like 4.5 liters per minute. A person that's bicycling very vigorously, it's 37 liters per minute. So put into the calculation that 544 times ratio times something that's another ratio of about 6 for the inhalation, and you start to see the magnitude of what can happen in terms of the hazard fields and what it means both for time, location, and the activity level while the person's in that field. So I think it's fair to say that for a long time in geography and other fields like urban planning, this idea of the time geography has been recognized as an important one, but most of the attempts to deal with it have relied on simulations that have a very weak data support, and they raise questions about whether or not what's actually being generated is going to be in sync with reality. But what we're seeing now, I think, is the first realistic opportunity to characterize these exposures with direct measurements on large numbers of subjects, or at least to have merged measurements with models so that we can better understand the time geographies of exposure and to understand these microgeographies of personal exposure and how we might use those in epidemiological studies. Let me just take you on a brief history of some of the instruments we use for measuring time activity. I don't want to date myself, but some of these instruments, like this one, go back to about 2003. I started using this, and this is it's called the Geostats Data Logger. It's like the size of a large camera. You'd have to carry it on your waist. It would run for about 18 hours, which was a lot of it was a battery pack, or something like this, a standalone eTrex Garmin global positioning system. So not particularly easy to use, not easy to carry, and not convenient for downloading onto a computer. Now, for about $70, I can get something like this. Now, that's wide-angle augmentation system corrected, so that basically you're able to look at not just the global satellite position, but there are ground stations that are giving you accuracy that usually is within about 5 or less meters. It's all Bluetooth enabled, so we can give these to subjects, have them wear them for long periods of time, download the data easily. And we often combine this with what's known as an accelerometer, which is something that has little pistons that move at different angles. It knows where it is oriented to the ground. And there's a whole science of how you can use this to measure physical activity very precisely. There's no question that these older and evolving instruments have been important. For example, if we wanted to look at a person's potential physical activity or their exposures that they might experience as they're moving through their daily pattern. This is from a child in a study that I conducted, and it's still ongoing in Southern California, where you have 650 parent-child pairs that have been measured repeatedly for their physical activity. And if they're like my kids, they're maybe watching video games or TV, so they have very sedentary behavior when they're in the home environment. And then they start going outside and they hit the park, and their activity level really explodes. So if we're concerned about, well, what makes children active, or when are they going to experience their exposure, there's no question that having this kind of information enhances our capacity to make causal inference much more than an association that would say, oh, their activity level, their odds of being moderate or vigorous in physical activity are 1.3 when they're in a park versus elsewhere, which is what this study shows. But you can see how that could be very convincing to have that kind of data. And just as an aside, this is not a real house. It's a real child. That's where we've moved the location of the house, because anytime you're dealing with these data, you are revealing the person's identity. And that's an issue that we have to come back to at the end when we discuss some of the strengths and limitations of these approaches. And then here's a traditional sort of pollution monitoring backpack where you might have being very bulky and heavy. It might run for 48 hours. Usually needs to be calibrated by trained staff. And it's going to restrict the person's regular movement. So against that backdrop, we've seen this rapid evolution of ubiquitous sensing. So there's an evolution of cyber social systems. I put my phone down so it wouldn't go off while I was in the talk, but I remember, maybe even as little as 6 years ago, I'd say, well, how many people in the room have a cell phone? I mean, now the question is how many people don't. Is there anybody that doesn't have a cell phone? There's usually one proud person who says, I don't have a cell phone. But no, right? So we all are carrying a system that's more powerful than the computer that I used to use when I was in graduate school. And what it's allowing us to do is have pervasive sensing of personal activity, psychological parameters, and ambient conditions. And as a futurist, Gibson said, the future's already here, it's just not very evenly distributed. So let's take a quick look at how unevenly distributed it is. And the idea of a UbiComp world follows Mark Weiser, a great computer scientist who worked for IBM Labs at Stanford in the 1990s. And he wrote a book called The UbiComp World that presaged the idea of ubiquitous sensing, where he said it would become the complete embedding of computational technology into our everyday lives. And so much so that we wouldn't even notice it was there. You know, how many people really notice their cell phones, right? It's just part of our lives. How many people notice all the video cameras that are honed in on them? I see one up here right now, right? So, now a lot of this is not being driven by an interest in the exposome. It's being driven by a worldwide revolution in telemedicine, which has now reached the level I looked at, and other fields, commercial applications related to mobile phones, Google and Apple. Just the healthcare sector is estimated to be a $10 trillion a year industry right now. So the amount of research and development that's going in there for profit motives is enormous. And we now have, well, this estimate goes back to 2017 when I did a review paper, but 7 billion cell phones globally, and more than 1.5 billion of those are smartphones. So I think we have something like 1.5 billion computers on the planet. So we're now looking at 4.5 times the number of computational devices that we're carrying mobilely. And I think what most people don't realize is that these smartphones have a tremendous array of devices that are capable of, trying to get a cursor in here, capable of measuring things in the environment, whether we want to measure temperature, humidity, barometric pressure, even heart rate, global positioning system, dissolved oxygen in the blood, inertia, proximity to other cell phones, ambient light. And these are all going into what's now a fairly powerful processing unit that can be displayed. And we've got storage and communication modules that allow you to send that information back to the web and back to central servers where it might be further processed. And I think when we look at the types of sensing that are available, it's useful to separate these into opportunistic and participatory. So opportunistic is where I'm not going to ask you to do anything. You just have to carry your phone. And this is what Google does all the time. It's tracking us continuously. Has anybody, just as an aside, have you got the electric scooters here yet? They're a real revolution in California right now, where there are tens of thousands of people that have these scooter shares, and they're electric scooters that people are riding around. We're interested in these things because they're disrupting the whole travel system. And I got my grad students to research about it, and it has nothing to do with transportation. It's a bunch of people that started a startup company in San Jose, and what they want to do is understand where you move and what your preferences are. So they have your age, your driver's license, they know who you are, they know where you live, and then they just want to see where you go so they can sell that information. So that's happening all the time on our phones and on other devices that we may choose to voluntarily carry. There's trip mode, so walk, bike, we can get this, and I'll show you out of the cell phones without asking for anything. Now, we get into participatory, we might also be able to get surveys that assess people's mood and affect, their gait and position. These things are becoming important, say, as people want to age in place. If somebody is trending toward a stroke, or they've just had a minor stroke and it's affecting their gait, this is something that you can detect through the phones. You can get noise, ultraviolet. So we can get all of that off the cell phone. We might also want to use the cell phone as a base station so that we can have microsensors that are using that to collect the information via Bluetooth or Wi-Fi, or Wi-Fi, sorry, I'll say it in European terms. And then standalone sensors, which we're quite familiar with, that can measure numerous ambient exposures and also biological functions. So we did a review last year looking at the types of sensors that were on cell phones. These are the 25 most commercially successful cell phones. And what immediately strikes you is a lot of them do have, sort of standard things that they put on there, like they all have accelerometers, they all have GPS. But you know, some of them can measure interesting things like ultraviolet light, dissolved oxygen in the blood. But there is quite a vast array of different types of phones, and the quality of the sensors that's on these phones is highly variable. So that really complicates it if we want to move to a world where all we just do is ask people to carry their phones, because the phones are very different. And that's a point that I'll come back to. So several years ago, some colleagues and I in Barcelona, Spain, got a small grant to try to see, well, what could you actually do to get information off of a cell phone that would help you to improve air pollution exposure assessment. So we started with a smaller study where we had 36 volunteers, and we equipped them with standard measurements. So we had there's the accelerometer I showed you earlier. The thing on her arm is called a body media senseware. It's another way of getting at physical activity, and it also allows you to look at arousal through galvanic skin response. So the temperature gradient of the surface skin compared to lower skin. We tried working with that data, and it was really kind of functionally useless. All I can say is people get aroused a lot, and we don't know why. It doesn't seem to relate to anything in their environment that we're able to detect statistically. And then we had them carry the cell phone and a global positioning system. And my colleague Edmund Cito, who was then at UC Berkeley, is now at the University of Washington, developed some software so we could extract out of the cell phone physical activity and geographic position. So basically, my colleague Audrey Dunazella, who's sort of a mathematical modeler, and I and others worked together to come up with a system so that we could harness the power of these cell phones. So we start with a standard land use regression or dispersion model that gives us ambient concentrations in a fixed sense. So it's a chronic surface of exposures across Barcelona. And then through looking at the information from the location and the activity, we were able to infer the person's activity level, because remember I said that's quite important for their inhalation. We then went to the literature and looked at indoor-outdoor penetration ratios for various types of air pollutants. And we calibrated this ongoing surface using government monitoring data. So it's sort of like the ratio of the background station to the specific hour and day, so that we're able to then characterize the up and down movement of that surface. And this gives us the capacity to look at personal exposures to air pollution. And then when we have the person's energy expenditure based on the accelerometer on the phone, we can then calculate their inhalation rate, so we actually move a step closer to what we really want, is their inhalation of air pollution. Because most of our epidemiological studies, for people that aren't in epidemiology, we assume that the person is a breathing machine that sits precisely on their front step for 24 hours a day, never moves, never changes their physical activity, and that that's somehow going to characterize their air pollution exposure. And it's amazing that it's worked. A friend of mine, Rick Burnett, is a famous statistician that does a lot of work in air pollution epidemiology, always says, gosh, with all the errors in our models, it's amazing we find anything. But we'd like to minimize that error so we have greater confidence in our results. So here's one volunteer and their air pollution map over 5 days. And these are called metabolic equivalent levels of energy expenditure. So higher energy expenditure would be coincident with running or riding a bicycle vigorously, going down to that lower level where it's in the white, where they're going to be quite sedentary. So one of the things that you immediately see here is that people cover a lot of territory over the course of a week, and their activity levels vary greatly in relation to the exposures. So what we found is that made a tremendous difference for trying to understand which microenvironments were important for conditioning their exposures. So if we look at their time spent in transit, it's about 6% of their total time budget, which is roughly in line with European and North American averages, plus or minus a few percent. It's about 11% of their exposure, because people are often commuting during high exposure periods, right? During rush hours, the cars are out, they're walking around. But in Barcelona, where about 50% of the mode share is by walking, and a fairly small proportion, about 2% by biking, but you've got more than half the people that are in active travel. That little 6% period accounts for 24% of their inhalation. We did a bigger study, so we were able to take that pilot study and go to the National Institutes of Health in the US and get some serious money so we could enroll 174 participants. And just staying focused on the travel, we see it's about 9% of the time in this, in that group. It's about 11% of their time-weighted average concentration, but again, 20% of their total exposure. And this is for PM2.5. It's a pollutant that doesn't quite have the same micro area variation as you would see with NO2, so we're getting slightly more muted results, but they're roughly in line. And then if Juan Pablo Arula can ever publish it, we'll put this out soon. He's a little slow publishing it, but I'm still pushing him, so we'll see. But the interesting thing here is, does it make a difference when we have this home-based exposure where we assume the person's a breathing machine versus an activity-based exposure? And yes, it does. It's about a 20% difference. Is that enough to affect the results of an epidemiological study? We don't know, but probably. And certainly we don't want to be consistently underestimating exposures when we're making public health policies, because we're probably going to allow people to have higher exposures than they would in the real world that they're living. And one thing I didn't realize when I started working with these data is how big they get very fast. So this is just 2 sensors pinging every 10 seconds over the course of a week. So that's the data from our 174 volunteers. And you can see what a dense point pattern that is. So we've got almost 11 million points of data, and the data are messy, right? They have got error in them. There's locational error. There's a lot of cleaning up that has to be done there. I was asked by the National Institutes of Health, they want to do a big million-person cohort study. How feasible is that to put cell phones on everyone? I said it's fine as long as you can deal with 61 billion data points a week that need cleaning. So, this becomes an enormous problem. And I have an ongoing grant with Sudipta Banerjee at UCLA, who's the chair of biostatistics there, where we're trying to look at ways of reducing the data cleaning and getting signals out of these data that are meaningful for characterizing exposures, because clearly we can't do the sort of hand cleaning we did on our smaller Barcelona sample. So what are some of the lessons here? Well, I think location and physical activity can be linked to exposure surfaces, so we're getting much closer to Hagerstrand's idea of the lifelines of exposure. And this information can be used for improving exposure estimates, but the data are very big, very messy, and there's a lot of work to deal with all of that. Now, another question is, are the data valid? Whenever we're using these lower cost sensors, we want to understand, are we getting information that's close to what we would get out of a research grade instrument? So we followed up with that larger sample and did a similar type of deployment where we have the CalFit software, the accelerometer, and the GPS is on your right. And then this just shows sort of typical activity patterns across a weekly period of 9 days. And this shows, you can see that there is regularity here, in this person's activity pattern where they're getting up and they have this burst of activity and it kind of goes down as they go to work. But there are irregularities there too, that as we move forward, that we have to be able to understand. We don't necessarily have to use all of the data, but we are going to have to use quite a bit of it to be able to characterize their exposures. So when we compare this to the Actigraph, which is the commercially available accelerometry instrument, these are the, in the red is our CalFit instrument, and in the black, the Actigraph. And you can see that we're tracking quite well, but we're losing some of the peak exposures. So we broke this down into classifying light, moderate, and vigorous activity. It's only in the very vigorous activity that we get this sort of systematic underestimation, but it wasn't significantly different. And we've now come up with algorithms where we think we can get that a lot closer. And then the locational accuracy, the GPS, the cell phones actually picked up a lot more locations than the commercial GPS. And that's because cell phones actually have what's known as an assisted GPS in them. So they're always seeing all the satellite array all the time. And they're using that to triangulate. They also have the cell phone towers themselves that they can do old school triangulation from with known distances. So you get a lot more locations, and the accuracy is very similar compared to, say, when we looked at known road locations where it was, the person couldn't be walking through buildings. They weren't supernatural, so there was air. And how often were they close to the roads and at what distance? And it was very similar. And when we looked at classifying key locations, we got accuracy was about 83% of the time. So when we look at what we got out of that study, I think we did get very good measures of physical activity that were comparable to the research instrument. And the GPS generally obtained more than the phone. But again, it was very messy and hard to clean. One of the differences here is the wear time. So it's very easy to put one of those belts on with an actigraph. You don't have to charge it or anything. But if people are absent-minded like I am, they forget their phone, they don't always charge it, that sort of thing. So I think it shows that these cell phones have the capacity to be worn, and they can be worn for a much longer period. So that's a big advantage, right? We're not distributing a research instrument to somebody. We're asking them to just carry something that they already carry anyway with slightly different software. The problem with all of this is that, Edmund and I are not business people, so to actually create an app is one thing. To maintain the app and put it out on the web and get people using it, that's a whole other marketing adventure. So what we're working with now is trying to understand what we can do with activity tracking from commercially available applications. And the one that we identified as sort of an industry leader is called Moves. And here's Moves characterizing my bike ride, the perilous one from my house in Santa Monica to UCLA. Not quite the same bike infrastructure you have in Lund here, unfortunately. But you can see that it's giving me a reasonably good trace of where I go. And then when we take an individual over a longer period of time, you can see that we are able to characterize their activity. But again, you're dealing with very dense, very difficult data. This is over about a 6-month period. And that's Jonah, my graduate student I showed you earlier. Now, we talked about the activity space. This is the 95% ellipse in that purple circle. And we're just showing the home and the work locations. And we can also extract out something known as a kernel density function. So we can show you where, on average, the people tend to be more active. So if we're trying to characterize population exposures, this kind of information could be very useful, right? Because we might not want to necessarily track everybody, but we'd like to know where, in general, individuals are more active. And we're still not sure, whether we can take this information and generalize it. That's a big part of what he's doing his thesis on. But I think it shows the promise of using even these commercially available applications. And what we're doing now is another validation study where we have people wearing the research grade accelerometer and GPS, and we're comparing it to what we get out of the Move software. So let me shift now to sensors that are not on the cell phone, but microsensors for measuring air pollution exposure. And this is based on a study that was part of that larger National Institutes of Health study. I teamed up here with Rod Jones at Cambridge University. He's an atmospheric chemist and one of the leaders in developing microsensors. And this is sort of an earlier version. He's got a better version of it now. But it's based on the alpha sense sensors, which are shown here, those 3 sensors. So it's nitric oxide, nitrogen dioxide, and carbon monoxide. And it has on board GPRS, so you can send information directly from this through cell phone signals and collect it to a central server. So we were interested in knowing, well, how well does this do when we compare it to a reference grade instrument? And this is the 2B Tech instrument, which would be about a 3,000 US, or say 3,500, say 3,000 euro instrument, and the Cambridge monitor is shown in blue. So again, we see something similar to what we saw with the accelerometry. We're able to detect a pattern that's very similar, but we're missing some of the peak activity. You can correct that though, that's a bias, and you can calibrate one sampler to the other. But we wanted to see, importantly for, I think, a epidemiological study or a public health study, how well can we differentiate microenvironments based on what we would expect to see in the exposure fields? And we scripted people to walk through areas that were beside the Mediterranean Sea and in parks where we expected the exposures would be lower than in a background area of Barcelona, which is fairly polluted. So the background is sort of our intercept. Sorry, this cursor is a little kludgy. So the top one is showing the parts per billion or parts per million of NO and CO in the background location. What we see compared to that is a significant reduction when we go into these areas where we would expect to see lower exposures. And then when we scripted them to walk through or stand beside low traffic and high traffic environments, you can see the low traffic, again, we're getting lower exposures than we did in that sort of urban background, which had a fair bit of traffic, but it wasn't like right over a highway or something. And then we scripted them to stand on a bridge above a known truck route. And you can see again. So, what we're able to show here is that there is the capacity in these sensors. They might not be perfect, but they are able to detect these microenvironmental differences with a fair bit of accuracy. And if you were interested, it was just summarized in a paper that I published last year. Now, it's not just for the gaseous pollutants. We can also measure PM, and I'm going to give you examples of both types of sensors. I know someone like Christina knows a lot more about this than me, so I'm humble to present anything on PM sensors in front of people with that kind of engineering expertise. But we have basically two types of sensors that we can have for low-cost microsensors. And one is fairly familiar to anybody that's worked in the field. It's a filter-based instrument, so we're going to draw particles with a pump through a size-specific inlet and deposit the particles for post-hoc paper analysis, where we might be able to do mass, chemical, physical properties, or both. And the other is a light scattering particle counter that's going to use lasers or other light sources and look at the attenuation of light against a known level of light that's being emitted and a white background to give us some estimate of the particles. So looking at that first type, this is a very interesting instrument that was developed by my friend John Volkins at Colorado State University, which is, I think, UPass University, something, aerosol system. I can't remember what the pass is, but anyway. This gives basically a small little inlet that's allowing particles at different sizes. It's got a microblower. It's very small. It's about this big. And it collects onto a 37 millimeter filter, and it has a lot on the meteorological conditions and also the capacity to send back information from cell phone signals. So there's the inlet, the filter cassette, the flow system, and a battery and a housing. And in validation studies where he's looking at, sorry that graphic didn't come through, he's working with Mike Brower from UBC and others to look at the impact of indoor cooking, which we didn't talk about earlier, but in Ethiopia and other parts of Africa and Asia, it's one of the biggest sources of exposure, particularly for women and children. And when we look at that big number of about 6 million or so deaths per year that Christina presented, it's a little less than half of those deaths that's likely to be attributable to these indoor exposures. But you can see when this is compared against the US EPA concentration, so-called federal reference method monitor, getting very good correlations, on the order of, the R is something like 0.996 and the R squared is 84%. So with these little instruments that cost about $400, you're getting the capacity to do a lot that's, going to give you information that is, if again not perfect, but very close to what you would get out of one of these research grade sensors. And what that's supposed to show, that X, is that he's testing it in chambers against known concentrations as well, so, and different types. And I think importantly with this, you can take the filter and then you can do chemical and physical speciation of it as well. And that's something that maybe for the Ethiopia study that Ebba and her colleagues want to consider, looking at how to use those. Because, at that price, you can put out a lot more of the monitors than you'd be able to. These don't give you the capacity, though, to look at those real-time incidents, because you're just collecting over a known period, like, say, a week. So we look at some of the lessons we can draw from the microsensors. There's definitely bias, unreliability, and extensive post-processing, but we do get pretty good correlations with reference grade. I think, though, when we start looking at the advantages of these low-cost microsensors, we have to balance it against the huge human resource processing cost, and that's not insignificant. So you might have a cheap sensor, but then you take a fairly expensive postdoctoral analyst and you have to put them on it for months to get that calibration curve put together. So I'd say when we look at these sensors, they're not feasible for these huge studies yet, but perhaps for smaller studies that are well resourced. Now, another big innovation that's occurring is the advent of citizen science. And what Mike Goodchild, who's kind of the granddaddy of geographic information systems, who also just happens to be originally from Canada and from McMaster University, where I used to work, is called volunteer geographic information. So what can we do to get people working for us that are working for free because they have an interest in the information that they want to collect? And I think, we think about this, there are really a couple of big advantages. One is the resource costs go down tremendously. If you can train the public to do this kind of monitoring, and you don't have to send trained technicians into the field, that's a huge savings for the researcher. But what I've discovered from working in this area for a while is that the people in the public often have information that we would never know. And the study I'm going to show you, the people that were on our sort of public advisory committee taught us a lot about the real types of exposures that were happening where they were, that if we were just coming in as Western researchers walking into an area, whether it's Ethiopia or the Imperial County of California, we'd never be able to understand that. So let me take you to the far southeast of California. We're abutting the Mexican border, and we're just up against Arizona. And this, I think, was the first community-based mapping and monitoring of air pollution in the world that was successfully implemented. And some of the vagaries of Imperial County, it's very poor. It has a very high population of new Mexican immigrants that tend to, for reasons that are not fully understood, have much higher asthma incidence, perhaps because of some of the exposures they're facing. And what they have that is, I think, characteristic of many of the places in Africa that we're interested in studying as part of this theme, they have agricultural burning that happens in proximity to residential structures. So it's a huge agricultural area. It gets sun almost all year round, so you just have to add water and you can grow virtually anything. Adding the water is another sensitive issue, but this is a shot of agricultural burning that's happening very close to where people are living. And then there's also something called the Salton Sea, which is sort of a geographic mistake that causes dust storms. And there's the Salton Sea. It occurred when the Hoover Dam was being constructed. There was an accident that spilled a huge amount of water off the dam, and it came and settled in this basin. And then because there was wasteful use of water in agriculture, that sustained the sea for many years, but they're starting to conserve on the water, and the sea is drying up, so you get these massive dust storms that, again, are fairly characteristic of what you might see in parts of Africa. So this shows the distribution of the government monitoring network in gray. So there are only 4 monitors, and then eventually our complete monitoring network where we had 40 monitors. So the government monitors at best are measuring by the day. They have one that measures by the hour. That's sort of set up as a research instrument beside one of those sites, but it's not a regular part of their network. So you can see immediately that we dramatically expanded the spatial and temporal coverage around the region. And a lot of that was made possible by people that were going out on Saturdays and at night that we trained. They're doing this for free to help us set up and monitor the instruments. And you know, you could say that this seems exploitive, but they really wanted that information because one of the things that these types of exposures are characterized by is very high spatiotemporal variation. So, you know, if somebody is burning on an agricultural field right beside you, the levels of particulate matter that we measured have sometimes exceeded 500 micrograms per cubic meter. During the dust storms, it's 900 micrograms per cubic meter. Just for reference, the Environmental Protection Agency 24-hour average is 35. So you're talking about levels that are way above health-based standards. And so they're concerned about their own health and the health of their children. And what we were able to do when we took this data into modeling is get these very fine-scale maps. So you can see some areas that are experiencing agricultural burning. You'd never detect this from the government sites. And we were able to use that network of low-cost sensors. And these are the optical sensors that I mentioned earlier. They're not the filter-based sensors. So we actually get information every minute. So we get minute-by-minute coverage. And we did an analysis that's still ongoing. And that is one of the frustrations of working with these data. You'll get a new calibration curve, and then you have to go back and redo all of your tables. I think that paper I showed you earlier with the Cambridge monitor, I redid the tables about 4 times before we really felt like we got the very best data we could. I was at my wit's end, nevertheless, but I'm glad that we managed it. So when we looked at just using that 35 microgram per cubic meter 1 hour, for 1 hour, not 24 hours, just as a sort of cutoff to say, well, we don't have an hourly standard for air pollution anywhere in the world that I'm aware of. The Air Resources Board, though, is currently conducting studies to look at this because they're concerned about those types of very short-term, very high exposures. But the government monitoring network detected about 703 episodes, and we detected 1,426. So this is a huge difference in the type of information that we can yield from these low-cost networks compared to what you're getting from traditional government networks. So if you want to warn the public about risks or you want to study those risks, clearly you're probably going to get more information from one of these embedded or ubiquitous networks. So the higher spatial and temporal coverage led to much better predictions of exposure that could be used in epidemiological and public health studies. And if you can imagine combining this with the locational and physical activity information, so you're getting a very fine-scaled exposure assessment with the activity, you're going to really improve those exposure estimates. But again, an underlying theme of all this, data is messy, voluminous, and difficult to work with, and we don't quite have the methods there yet for doing that. Now let me take a look now at the sort of idea of biomonitoring so that we can get very good assessments of when people are actually experiencing symptoms. And this is all part of that telemedicine revolution that I talked about. And I don't think we really even see it that much in a lot of the developed countries, right? We can go to the doctor. In the US now, I get everything over the internet back from my doctor, all the test results. If I was in a more primitive place like Canada and their really backward healthcare system, I still have to call the doctor for all that. But we don't really deal with telemedicine that much where we're having an interview with a doctor over the internet or something like that. If you're in Uttar Pradesh, India, I had a student at UC Berkeley who did a study on this. And Uttar Pradesh is a very big place. It's like 180 million people, you know, so bigger than most countries in the world. Most people there are spending about $30 a year on health care. And most of that is women going for reproductive sterilization and operations, you know, if you average it out. So they're not getting a lot of health care. If you wanted to increase access to them, clearly the brick and mortar idea of building clinics is not going to be easily accomplished. So there's, you know, if you can get people in Uttar Pradesh to have video access to doctors, to use any of this information to send information back to their caregiver or physician, and they get technical assistance and training so they can treat their own illness or have somebody that's a medical technician treat it, you're going to greatly improve their quality of life, right? And you're also, if you're a private sector company and you can get at something like $10 out of that $30 and you've got 180 million people, you've got a really big number there. You've got a $1.8 billion revenue stream. So you can see why there's so much growth in this area. And I've been working with people at a company that was started by one of my former postdoctoral students, Meredith Franklin. And this is essentially an asthma control system that allows the caregiver to understand the environments in which the asthma symptoms are being experienced. So this is a short-term bronchodilator, so it's a rescue medication with a GPS attached to it that goes to the cell phone and then beams information back to the caregiver. So we've been using that to try and understand, well, what does that tell us about where people are having their symptoms and where there's an environmental cause to that? And this is a study with about 1,000 people in Louisville, Kentucky. And we looked at it in relation to nitrogen dioxide and ozone exposures. And ozone is, well, nitrogen dioxide, it's a secondary pollutant except when it's coming out of diesel engines where it's primary. But it forms very near to source. So you can think of this as a good marker for near source combustion. Areas where you have high traffic density, you often see a lot of nitrogen dioxide very close by. And roadways, of course, gradients. Ozone, on the other hand, because of the atmospheric chemistry, tends to form downwind of source and follows this sort of mirroring pattern of nitrogen dioxide because the two react, or nitrogen oxides react with O3 to produce NO2 and O2. So effectively what you have is a mirrored pattern of exposure. But what you're seeing here is not the pattern of exposure, but it's the pattern of where the people are using their asthma medication in relation to the air pollution exposure. So in those days where we have high ozone, we can see that it's in those suburban areas where we know ozone is high that we're getting all the asthma medication being used. On days where there's relatively low ozone and higher NO2, all of the risk is characterized by that NO2 area. So I think when we start to try to think about causality and trying to link up what's driving those asthma exacerbations, this gives us a much stronger basis for causal inference because we're then able to say, no, there's no gap in time or space or anything. It's at immediate moment we can see that those symptoms are occurring and we know exactly where they're occurring in time and space. So I think that's pretty exciting. We got it reviewed in Nature. We got 5 out of 6 good reviews, and there was one person that didn't like it, so we didn't get in. That's the way it goes in Nature. But we're trying other places, so hopefully you'll see that in the literature fairly soon. Now let me shift. I've talked a lot about microsensors, and I'd be remiss if I didn't talk about the revolution that's going on with remote sensing. Satellite-based sensors that are able to detect aerosol and gaseous pollutants from space. And this is part of a really fun study that I've been involved with that's being led by David Diner, the Jet Propulsion Lab. And he's funded by NASA, the space agency in the US, to launch a satellite, which is called the Multi-Angle Imager for Aerosols. And the idea is that we're going to look at areas with different atmospheric conditions, different subpopulations, and try to come up with estimates of speciated particle concentrations at high resolution on the ground. every, say, 1 to 3 days, depending on whether the area is considered a primary, a secondary, or a broader calibration validation target. So, yeah, darn, I'm sorry that some of the graphics are not working out here, but this just shows the areas that we're going to study, and one of them is in Ethiopia. So there you're seeing the differences in the particles per microgram per cubic meter. And what these are intended to show is they're all pie charts showing that there are vastly different compositions of particles in these places. But what we're trying to do is extract measurements of sulfate, nitrate, organic carbon, black carbon, and dust out of the satellites. So there's been a lot of work on satellites for characterizing ambient PM2.5 levels or PM10 or some gaseous pollutants, but not many that have looked at speciation. So we have this spectrometer camera that's picking up infrared and shortwave infrared that's going to be on board the satellite. So it's a commercial satellite that's being launched, and ours is one of many instruments that's on it. And I'm not a satellite engineer, so if you have really detailed questions about this, I'd be happy to take them back to David Diner and get them answered for you. But essentially, we've got this multi-angle viewing at the Earth, which goes plus or minus 70 degrees. So you can think of it as the satellite's taking a shot at this angle, and then a shot at that angle, and a shot at this angle. And the more angles you have, the better opportunity you have to characterize the aerosol that's in that given location. And it also is, because we're increasing the spectral bands that are going to be covered, we can use that information to get at the composition of the, and we also have a polarimetric, so a light refractor that's on this. So we have this long track and cross track, so it's shooting from angles like this and like this multiple times at the same location as it flies in a polar orbit. And the idea is we're going to take the satellite instrument, we're going to have some ground monitors, and this is something that Eva and Christina and I have to talk about, because we have to get some ground monitors if we want to convince them to target the satellite on Ethiopia. I think I've almost convinced them, but still working on that. And then we're going to have atmospheric chemistry models that we merge with the satellite images, because we want to get estimates that are not just every 1 or 2 days, but preferably every hour. So we're going to find ways of statistically assimilating those information together. Then we're getting the health records either from existing administrative databases or prospectively collected, and then we're linking it to PM and trying to see what the health effects are in targeted areas around the world. So this just shows some of the major cities that are being studied and whether they're acute, subchronic, or chronic exposures that are going to be studied. You know, of course, we have a lot more information in North America and Italy, but we don't want to just look under the lamppost. That's part of the power of having one of these satellites, and we want to characterize the exposome and air exposures. We want to go to those places where there's been a virtual blackout, like Africa, so that we can better understand what the health effects are like there. So let me just conclude with a few thoughts on some of the challenges with these sensors. I mentioned this earlier, privacy issues. If we know someone's time activity pattern, we know a lot about them. And there have already been divorce cases in California where people are using some of this information to say, oh no, you weren't by your office, you were across the bridge in San Francisco and your purported mistress happens to live there, or lover, to make it a gender specific or gender neutral term. Data ownership and protection. So what happens to these data once we collect them? Who owns it? And that's a big issue, because these data can be kept in perpetuity. Part of that incomprehensible data agreement you make with Google says we don't keep the data for that long, but we will use it while we have it. There's really no legal framework for covering this, and I was at this National Academy of Science meeting on the use of new sensing data, and we have one of the best lawyers in the world talking about this. And he was asked, well, what's the dark side of all these sensor data? And he said, well, you can think of it as, I said, well, it's the new Chinese system of social capital where they're tracking not just you with video cameras and all the other sensors, but they're tracking your social network. And if you're in a social network they don't like, they'll hold that against you, and you might not get a loan for a car. That's a dark side, definitely. But the lawyer had a different take on this. He said the dark side is that these sensors have so much potential for protecting public health and producing social good that we just won't use it because we'll be too concerned about the privacy issues because we haven't done enough to develop the institutional frameworks around the use of these data. So that's certainly, I think, another concern. Another thing is, how do we foster the idea of this participatory sensing or the community-based sensing in a way that's not going to give us horribly biased samples? So it's only people that are, sort of techies that would want to understand their patterns. That we want to get a broader assessment. So there's a lot of social science research there. Analytical, the data are super messy. So there's a lot of missingness. There are a lot of errors. How do we deal with that when it's streaming at us in billions of points, per week or per day? And how do we deal with bias sampling? We almost have to flip our traditional idea of statistical sampling as I'm going to take a smaller sample out of a larger population, and I'm going to argue because the distribution of that sample is going to be close to the broader distribution that I can make inference about this broader group from a smaller sample. Here we might have a sample that's almost the whole population, but it's going to be partly biased in time or space, or we're going to be missing key groups. So how do we deal with that analytically? And we don't have good methods for doing that. As we saw with Maya and with a lot of the other examples I gave you, you can't just measure everything. But how do we take it and mesh it with our existing models so that we get a better assessment of exposures? And that's something that there's a lot of work to be done there because there are what are called change of support problems. I might have the satellite at 1 kilometer, but then I've got the GPS every 10 seconds at a matter of meters. How do I mesh that together when the support level is very different on those data? And how do we think about analyzing too much data rather than too little? Because that's always been our problem in exposure science. We're taking little samples and trying to analyze it and find ways of saying, this probably is representative of what I want, but we're going to have too much data very soon. So just in conclusion then, I think, when we think about lifelines of exposure and the exposome, measuring physical activity and geographic location is critical to getting at that. And we can do that now with these ubiquitous sensors. The variable and types of quality on the cell phones is going to pose challenges in the near term. But we had mentioned from Ebba of leapfrogging, and leapfrogging is happening in Africa. Most of Africa doesn't have landlines. They have very high cell phone penetration on the order of 80% or more. A lot, so things are changing very quickly, and we're going to see these sensors improve. When we look at the microsensors, they're certainly getting there, but they're not there yet for large deployment. Citizen science is a really important innovation, and we need to find ways to foster that and to understand what the strengths and limitations are there. The satellite data, there's no question, the trend there is toward much higher spatiotemporal resolution and toward speciation. So being able to speciate the atmosphere from space is going to allow us to understand a lot of those areas of the world, particularly Africa, that just don't have, and they won't have in the near term, the ground-based monitoring. So I'd say we're not there yet, but thanks to the inspiration of Hagerstrand and Lund University, and now all the technologies that we've seen developed after this, we are moving toward a time geography of exposure. So I'd be very happy to take questions. I think I ran overtime there. I do apologize. I'm still in a different time zone, so I'll make that my excuse. And I want to acknowledge all the funders and people who have helped me, and then the people on the Maya team. So, and most of all, thank you for inviting me here and for your time today.
Thank you for a wonderful talk. It was very interesting. I'm wondering about the issue you brought up about handling big data sets, which of course is very common now in epidemiology, and I come from the omics field. And I was wondering if you've considered using machine learning techniques to process your data and analyze your data set.
Yeah, definitely. And I didn't have time to show it here. And maybe I'll do another talk while I'm here on some of the work I've done on wildfire modeling, where we're using the machine learning to assimilate a lot of data from satellites, from ground level measurements, from meteorological stations, and bringing that together to get optimal predictions. The processing of the GPS data with machine learning is another thing that we can do, but usually the machine learning is best for prediction rather than sort of classification. So, I mean, there are ways of classifying different types of activity, and we're looking at that. But I think a lot of moving forward with the grant I mentioned with Siddhitu Banerjee, so we're looking at using Bayesian methods where we can take prior information and say, for example, we know that people regularly go to work between certain hours, and this is where they work, or we can ascertain that. We can use that information to pull priors out that constrain their activity space for that time of the day. So we're not trying to work with those data. We're trying to work with things that are outside their normal activity patterns, because we might not need to characterize that every day. I think that's sort of the direction we're trying to move in, is to get a better understanding of these overall activity spaces, and then to be able to use that as a prior that's going to constrain a more broadly searching machine learning focus. So those are a few of the things that we're working on, but I don't think anybody has the answers yet, but that's sort of my initial thoughts.